The last thing that we're going to talk about in this section is a process called logarithmic differentiation. And the reason we care about it here so much is that it can make the process of finding a derivative easier if we need to use multiple derivative rules. So some of these problems, if I was to take the derivative like we normally have using our product rule, our quotient rule, our chain rule, some of these problems may require 2, perhaps even 3 or 4 derivative rule all at once. Perhaps it's 2 product rules, a quotient rule, and a chain rule. And if I didn't have this process of logarithmic differentiation, it would be very, very difficult to take the derivative of it. So let's talk about the process, the steps that are involved in that. The first step, you are going to take the natural log of both sides of your function. So you'll just apply the natural logarithm to each side of your function. That's fairly straightforward. The second step, I want to use properties of logarithms to simplify the more complicated side. One side will just be, y equals or f of x equals. It's really this side over here that I'm interested in simplifying, that more complicated, probably the right-hand side. And I'm going to simplify those using these 3 logarithm properties. You may recognize them from college algebra or a previous math class, but in case you don't, if we have natural log of a times b, so if we're multiplying 2 factors inside of our natural logarithm, we can break that up into 2 simpler logarithms by saying natural log of a plus natural log of b. If I have natural log of a divided by b, again, I can split that up into 2 simpler logarithms. I can rewrite that as natural log of a minus natural log of b. And then lastly, this one's a little bit different. If I have natural log of a to the p power, I can take that power and write it as a factor. I can say that's p times natural log of a. So in all of these equations, all these properties, we're always taking something that looks more complicated. We're taking that one single logarithm, and our goal here is to try and break it down and rewrite it so that we have more simple logarithms. So we're trying to simplify these logarithms as much as we can. We'll have more terms and we'll have more logarithms to worry about, but each one of those logarithms will be much, much easier for us to work with than just working with the original function, or even worse, the logarithm of that original function, because that also would add a 4th or 5th or 6th derivative rule that we would need to use. So once we have used our properties of logarithms to break this up, simplify that side as much as we possibly can, then we're going to take the derivative of both sides. Remembering to use the chain rule, we're going to be utilizing the chain rule quite a bit here for this section. And in particular, I just want to point out that we make sure to remember to use the chain rule on this y equals or this f of x equals. If I were to take the derivative of f of x, this is really implicit differentiation. If I was to take the derivative, not of f of x, of natural log of f of x is really what I would have. If I was to take the derivative of this, I really have implicit differentiation here because f of x is just another way to write y. So when I take the derivative of this left-hand side of my equation, I'll end up with 1 divided by f of x times f prime of x, or perhaps more simply, f prime of x divided by f of x, or if you prefer using y, we can also write it that way too. We can say y prime over y. So that is the left-hand side. The right-hand side, again, we'll still be utilizing the chain rule many, many times, multiple times, just depending on how many terms that we have. But I think utilizing it on the other side, that right-hand side, will be a little bit easier to see. This natural log of f of x is a little bit more subtle, and I think it's just easy to overlook. Lastly, second to lastly, I'm going to multiply both sides by f of x. I'll say or y, depending on the notation that you use. So I'm going to multiply both sides by that function. And essentially, the reason we're doing this is if you look at what we have here, right, we're going to have f prime of x divided by f of x on one side of my equation equals a bunch of other stuff over here. I really want to get f prime of x by itself. I'm trying to find the derivative, so I'm just going to multiply both sides of my equation by f of x to get rid of that denominator, and then that would leave me with f prime of x, which is exactly what I want. And then here, finally, my last step, I am going to substitute for f of x. So I'm going to take my original function and plug that in for f of x. You do not need to worry about simplifying this end result at all, because the end result will be very messy. I won't even try to simplify it most of the time because it is such a pain. So it's usually just not worth it to simplify it. We'll just leave it. It'll look ugly, but the process overall of finding the derivative is much, much easier. So let's look at a few examples. First up, I have f of x equals cosine to the 10th of f of x divided by 5x plus 3 to the 6th power. If I was to take this derivative without using logarithmic differentiation, this problem would require, let's see, a chain rule for the numerator. So this would require a chain rule for the numerator, a chain rule for the denominator, and then a quotient rule for the overall fraction. So I would have a chain rule, and a quotient rule. I would be utilizing 3 different derivative rules, which can be very overwhelming. It's not to say that you can't do it, it's that it's a very difficult process. So instead, this is a good candidate to use logarithmic differentiation. So let's start here. I'm going to try and show my work here as much as I can, show each of the steps. First thing I'm going to do is I'm going to take the natural logarithm of both sides. So I'll have natural log of f of x on the left-hand side and natural log of cosine to the 10th of x divided by 5x plus 3 raised to the 6th power. So all I did was take a natural log of x of both sides. My next step, I'm really looking at this side, and this is really one really complicated logarithm. I'm trying to break this up into multiple simple logarithms, trying to break each of these logarithms up into as simple pieces as I possibly can. So first, I see this fraction right here. I'm thinking about that second logarithm property. On the left-hand side, this isn't really going to change at all. It's just going to be natural log of f of x. But on the right-hand side, I see natural log of cosine to the 10th of x minus natural log of 5x plus 3 raised to the 6th power. So I've taken this one very complicated looking logarithm and I've broken it up into two, well, I won't say they're simple, but simpler logarithms that are a little bit easier for us to work with. Keep an eye out for any powers. So I see this power of 6. I see this power of 10 right here. Remember that I can rewrite those as factors using that third property of logarithms. So I think over here, this one's a little bit more straightforward to see. This one's a little bit trickier. But remember that when we say cosine to the 10th of x, what that really means is cosine of x, all of that raised to the 10th power. And then as soon as you write it like that, I think you say, oh yeah, I see it now. I see that whole inside part is being raised to the 10th power. So the left-hand side I'm going to leave as natural log of f of x. On the right-hand side, I'm going to rewrite that 10, so I'll have 10 times natural log of cosine of x. So I'm just taking this power and rewriting it as a factor. And then I'm going to do the same thing over here. I'm going to take this power of 6, I'm going to rewrite it as a factor here. So minus 6 times natural log of 5x plus 3. And the goal here is to break down these logarithms as much as we possibly can. You want the parts that are inside of these logarithms to be as simple as possible. So when I look at this natural log of cosine of x, there's no multiplication there, there's no division, there's nothing I can really do. I'm kind of stuck with that, so okay, that's fine. And then over here, 5x plus 3, I can't break that up. I see, maybe you see this multiplication of 5 and x, but because of this plus sign, because of those multiple terms, I can't do anything with that. So 5x plus 3, or natural log, excuse me, of 5x plus 3, that's as simple as it gets. So that was my step 2, and this is one of the longer steps, along with step 3. Here's where the magic happens. This is where we're going to take the derivative. So over here, derivative of natural log of x, and actually let me do this in red so that we know we're talking about the derivative now. Derivative of natural log of f of x, we said, hey, remember that you're using the chain rule right there. So when I use the chain rule, I'm going to have f prime of x divided by f of x, remembering that f of x is a function of x. That's literally what it stands for. Over here, I'm going to have a chain rule for this piece right here and a chain rule for this piece right here, but I think that's easier to work with than using a chain rule and a quotient rule all at the same time, because now I can look at this chain rule separately from this chain rule. I'm not trying to do so much at once. So on the right-hand side, 10, that's a constant multiple. That just comes down. Derivative of natural log of cosine of x. Let's see, that'll be 1 over cosine of x times the derivative of cosine of x, and I know that is negative sine of x. Minus 6, again, that 6 is a constant multiple, just comes down for our derivative. Now I want to find the derivative of natural log of 5x plus 3 using our chain rule, using our shortcut for the derivative of natural log of x. I know that that's going to be 1 over 5x plus 3 times the derivative of 5x plus 3, which would just be 5. You can also, so we can write it like this, you can also take that negative sine of x and put that in your numerator, say negative sine of x, and then same thing over here with this right-hand term. I could take that 5 and put that in the numerator as well. So you can maybe simplify a little bit here. You know, maybe we say that this is negative tangent. Honestly, I don't even know that I would bother. I might just say, well, this is negative 10 sine of x divided by cosine of x, minus here, maybe I'll say, okay, well, 6 times 5, I know that's 30, that's 30 over 5x plus 3, but I wouldn't bother trying to find a common denominator or anything like that. I would probably just leave it as it is, but we're not done here. Because remember, the end goal here is to get f prime of x by itself. Right now, I don't have that. I still have f prime of x divided by f of x. I want to get rid of this f of x that's in the denominator. So I'm going to multiply both sides by f of x. So this is my step 4. I'm just multiplying both sides by that f of x. So on the left-hand side, these two will cancel, which is exactly what I want to happen. So I'm left with just f prime of x. Well, what's on the right-hand side? I have what I started with. I have this negative 10 sine of x divided by cosine of x. Again, you could write this as tangent of x if you wanted to. Minus 30 over 5x plus 3. That part just comes down. And I'm going to multiply that by f of x. Well, shoot, what the heck is f of x? What does that part look like? Look back at what we started with. Hey, right there it says f of x equals cosine to the 10th power of x divided by 5x plus 3 raised to the 6th power. I'm literally going to take this piece right here, my original function, and just plug that in for my f of x. So times, and I'll do this in red just so that we see that this is all one expression, times cosine to the 10th of x divided by 5x plus 3 raised to the 6th power. Parentheses will be really important, so we need to remember that we have parentheses around that negative 10 sine x over cosine of x minus 30 over 5x plus 3, because in the end of this problem, right, I want to be able to take this f of x that I just wrote here, and I'm not going to do it, but I want to tell the reader that, hey, we're really multiplying both of those two terms by the original function, not just that last term there. Boy, that looks ugly, and I don't really want to simplify it. And actually, that was my step 5, is to substitute my original function in for f of x. And this is the part where I say, you know what? Don't worry about simplifying this at all. It's really ugly. You might be able to simplify it, yeah. Is it worth it? Absolutely not. No, I would not bother. So this is my answer. This is my derivative. Be careful if you're typing these into MyMathLab. Make sure that you keep track of your parentheses. I think that is going to be a tricky part of this problem. Not to say that the rest of it isn't tricky, but it is something that we're just going to have to keep track of. Let's look at another example. Got a couple more here. Next, I want to use logarithmic differentiation to find the derivative. Actually, let me just separate this. My function is, oops, I still can't see it great. There we go. I want to take the derivative of f of x equals x squared plus 1 to the 4th power times e to the x divided by x squared plus 4. Really ugly function. And if I wanted to take the derivative of this just kind of like we normally would, just kind of go out full steam ahead, this would require a chain rule for this part right here, a product rule for this numerator, and then a quotient rule as well for the fraction. So I would be using a product rule, a quotient rule, and a chain rule. The trifecta, right? All of my derivative rules. I would be required to use every single one of them. That's a really ugly process. It would be a lot easier to use logarithmic differentiation. So I'm going to exactly start like I did last time. I'm going to start by taking the natural logarithm of both sides. I'm going to take natural log of f of x, set that equal to natural log of the right-hand side of my equation, which is x squared plus 4 raised to the 4th power times e to the x divided by x squared plus 4. So there's my first step. My second step, I'm really focused in on that right-hand side. I really want to use my properties of logarithms to break that up as much as I possibly can. So my second step, the left-hand side I'm not going to change. Not doing anything over there. The first thing I see on that right-hand side, though, is the fraction. So I'm going to utilize that second property of logarithms. Natural logarithm of x squared plus 4 to the 4th power. Oops, excuse me. You know what? I made a mistake, didn't I? I said x squared plus 4. I really meant x squared plus 1. Let me fix that. X squared plus 1 to the 4th power divided by, times e to the x divided by x squared plus 4. So x squared plus 1 to the 4th. What else do I have in there? I also have that e to the x. So times e to the x minus natural log of my denominator. There I just have natural log of x squared plus 4. So here is the first step, but I'm not done. I can actually still simplify this a whole lot more. And I'm looking at this first logarithm in particular. I see x squared plus 1 to the 4th power times e to the x. Again, read that out loud to yourself if you need to. Say what you're doing. You're multiplying those two together. I have x squared plus 1 to the 4th times e to the x. So I'm going to break this piece up into two separate logarithms again. I'm going to say natural log of x squared plus 1 to the 4th power plus natural log of e to the x minus natural log of x squared plus 4. Okay, and I'm going to say, can I simplify any of these logarithms anymore? Because that's what I want to do. And I see, well, yep, I see that power, x squared plus 1 to the 4th power. I absolutely can simplify that. I can bring this 4, I can rewrite that as a factor. So this is really 4 times natural log of x squared plus 1 plus, this piece is really subtle, natural log of e to the x. It's really easy to overlook, but remember that natural log of e to the x, remember that the exponential and the natural logarithm are inverse operations. They will cancel each other out. I'm actually just going to be left with x in that middle term. Be careful with that one. It's really, really easy to overlook. Minus, I can't really do anything with that last term. Let's leave that as natural log of x squared plus 4. So that's just my right-hand side. My left-hand side I haven't changed at all, so this is natural log of f of x. Whew. Okay, that's the end of step 2. Step 3, here's where we're going to take the derivative. So again, natural log of f of x, I need to remember to use my chain rule. So let's see, I should have f prime of x divided by f of x equals, on that right-hand side, I am going to have to use the chain rule here and here, but I think it's a little bit easier to see. 4, that constant multiple just comes down, times the derivative of the inside part, the derivative of x squared plus 1, that would be 2x, divided by that inside part of x squared plus 1, plus the derivative of x. Well, here I don't need to do anything fancy. That's just a power rule. Derivative of x, that's just 1. Minus, over here, natural log of x squared plus 4. There I am going to have to use the chain rule once again. Derivative of the inside part will give me 2x divided by that inside part of x squared plus 4. And we can maybe clean this up. I might say, well, 4 times 2x, that's 8x divided by x squared plus 1 minus 2x divided by x squared plus 4. And I wouldn't simplify it any more than that. I wouldn't try and find a common denominator. I just wouldn't touch it at that point. On the left-hand side, though, again, we still have f prime of x over f of x. Keep in mind what we're trying to find. We're trying to find f prime of x. So we got to get rid of this f of x. The way we do that, we multiply both sides by f of x. This is our step 4. So my last step then, on the left-hand side, f of x is cancel. I'm left with f prime of x. That's exactly what I wanted. On the right-hand side, I have 8x divided by x squared plus 1 minus 2x divided by x squared plus 4 times f of x. Here's where f of x is coming in. And remember, f of x, it's just my original function. That's this piece right here. So x squared plus 1 to the 4th power times e to the x divided by x squared plus 4. So I have x squared plus 1 to the 4th power times e to the x divided by x squared plus 4. Again, just make sure that you have parentheses around that first part of your derivative. We want to make sure that we include those, otherwise we will get the problem wrong. But at this point, we don't need to simplify it anymore. This is our solution. We are not going to do anything further with that because, boy, that is an ugly derivative. So I won't say that these problems have been easy, but I think that they are easier through this process of logarithmic differentiation. The process is still pretty lengthy. It's 5 steps long altogether, and there's chain rules, and I got to know these properties of logarithms now, but it is much easier than the alternative, than utilizing multiple derivative rules at once, which is, I think, a very difficult thing to master. Let's look at one more example. Looks like a fairly simple function. Here it says let f of x equals x to the sine of x power. Notice in this case, I'm not saying use logarithmic differentiation to find the derivative. In some cases, I will say, and on the exam, I will include at least one question that says use logarithmic differentiation. And I expect you to use logarithmic differentiation. If you don't, you will not receive credit for that problem. But here for this problem, it doesn't say to. But this is a really good candidate for it anyway. We can use logarithmic differentiation even if it doesn't say we have to. Because I'll get the same derivative no matter what. You might look at this and say, well, boy, that doesn't look too bad. X to the sine of x power, that's going to be a power rule. And I'll say, well, hold on a minute there, guy or girl. Look at that power. It's sine of x. You can't use the power rule because sine of x is not a constant. We can't do that. There's really not a great way to deal with that right-hand side. I think that if we're finding the derivative, if we're finding f prime of x, I think that looking at this right-hand side and saying I have x raised to some power, maybe I'm not sure where to go with this, I think this is a really good candidate for logarithmic differentiation. So my first step, I'm going to take the natural log of both sides. Let's try it out. Let's see where this goes. Natural log of x to the sine of x power. I'm going to use properties of logarithms again to split that right-hand side up. So on that right-hand side, I'll have sine of x times natural log of x. On the left-hand side, natural log of f of x. So now I've simplified this right-hand side as much as I possibly can, just like we've done before. I'm going to use properties of logarithms to I'm going to take the derivative now. I have used properties of logarithms. I need to take the derivative now. On the left-hand side, again, be careful. Don't forget about your chain rule. We'll have f prime of x divided by f of x is equal to, over here, keep your derivative rules in mind. This one's a little bit tricky because we're not using the chain rule. We're actually going to use the product rule here. This says sine of x times natural log of x. So the derivative of sine of x, that will be cosine of x times natural log of x, plus this times sine of x stays the same, but I take the derivative of natural log of x. I know that is 1 over x. So I have f prime of x over f of x. This is equal to cosine of x times natural log of x plus sine of x over x. This isn't what I wanted, though, because remember what I want at the end of this is f prime of x. I'd really like the derivative. So I need to multiply both sides of my equation by f of x. That'll give me f prime of x on the left-hand side, which is exactly what I want. And on the right-hand side, I'll have cosine x natural log x plus sine x over x times f of x. Well, what was f of x? That was x to the sine of x power. So this is x to the sine of x power. There's my derivative. That's all I'm asking you for in part A. At this point, I've used logarithmic differentiation. I found the derivative. This is my solution. The next part here, part B, says find f prime of pi over 2. Here we would take pi over 2, plug it in for x. And just to show that these derivatives are nasty, let's actually show that here. If I wanted to look at f prime of pi over 2, I have cosine of pi over 2 times natural log of pi over 2 plus sine of pi over 2 divided by pi over 2. All of this multiplied by pi over 2 raised to the sine of pi over 2 power. Cosine of pi over 2, that's actually just 0 times natural log of pi over 2, so this term is going to drop off. Plus sine of pi over 2, that is 1 divided by pi over 2. We'll have to simplify that in just a second. And then all of this to the pi over 2 raised to the sine of pi over 2. Sine of pi over 2 is just 1, so to the first power. So I essentially have, actually I'm not going to simplify it, I'll have 1 divided by pi over 2 times pi over 2. These two cancel, and oh my goodness, look at this. My answer is just 1. How nicely that worked out. I was worried there for a second. But I think getting to that point, right, working with this derivative was not the easiest thing in the world. It's a really ugly looking derivative. So generally when we use logarithmic differentiation, we won't be doing much with the derivative after the fact because the process of finding that derivative is so messy. Because the end result is so messy, we won't be utilizing the derivative all that much. We can use the derivative in other problems that are perhaps easier derivatives for us to work with.